This is going to be a walkthrough of problem 1 on page 8 of the student note packet, which is the first problem of the vectors word problem extravaganza. So if you're struggling getting this one started, you'll have other static equilibrium problems as we work through the rest of the unit. So this is kind of just like a good refresher if you aren't familiar with static equilibrium or what it does. So we have this diagram here at the top of page 8, and this is the diagram we're going to use with this problem. And we're told that a box of supplies weighing 1,200 pounds is suspended by 2 cables attached to the ceiling as shown in the diagram. And we want to figure out what the tensions in the 2 cables are. So what is the force vector there that they're pulling at in order to keep this whole situation in static equilibrium? So one thing to note about static equilibrium, this means that nothing is moving. So that box is not moving downward, it's not falling, everything is stationary. And that's really important about static equilibrium. So the other thing that we can conclude then is that all of the forces in the I direction or all of the forces in the horizontal direction sum to 0, and all of the forces in the J direction or that vertical direction are also going to sum to 0. So the first approach I'm going to take for this problem is breaking each of these forces into their horizontal and vertical components and then solving for the 2 force vectors using that. And then the second approach I'll take is rearranging everything to fit the tail to head method. And you guys can kind of pick which option you like the best. So the first thing I'm going to do though is I'm going to lay a set of axes out over my picture, over my diagram here. So I'm going to drop the y-axis there, and then I'll call this the x-axis. It's kind of already set up for us like that. And I'm going to color kind of all of the forces that are acting or the forces in play. So that first force sitting in the first quadrant there, I'll call that F1. And then the second force we have acting on the box is this force here. I'm going to call that F2. And we're told a couple of things, right? We're told the angles relative to the ceiling that these forces are pulling at, which become really useful when we're going to break these up into the horizontal and vertical components of the vectors. And then we have one more force vector, which is a little less obvious, and that's the force vector created with the box. And that box weighs 1,200 pounds, and all of that is being pulled down. So this is force 3, and that just has a force of 1,200 pounds because that's the weight of the box. All right, so static equilibrium, we go back to that, right? Static equilibrium. I'm just going to make a note. Everything sums to 0. So what I'm going to do is I'm going to break all these forces into their horizontal and vertical components, and then we'll sum all of the horizontal components together, set that equal to 0, sum all the vertical components equal to 0, and then we'll solve the system of equations. Okay, so our first force, we don't know its magnitude, so I'm just going to call that force 1. You could also call it X, might be a little bit easier, less to kind of write out. Actually, maybe that's what I'll do here as well. All right, so I'm going to call the magnitude of force 1 X. And I'm going to do the same thing for force 2. I'm going to call the magnitude of force 2 y, just so I don't have to write as much when I go to write all of the components out. All right, so force 1, we know in order to break something into its horizontal and vertical components, we take the magnitude, which we're calling x here, multiply it by the cosine of the angle in standard position, in this case 45 degrees, because it's 45 degrees from the positive x-axis. That's the I-hat direction. And then again, magnitude times the sine of 45 degrees in the j-hat direction, or the vertical direction. Okay, force 2, coming along here, it's horizontal vertical components. Now we call the magnitude of force 2 y, so that's y times the cosine of this angle in standard position. So measuring from the positive x-axis, going counterclockwise, that's 180 minus 30. So this angle in standard position is 150. And then that's the I-hat. And then y times the sine of 150, j-hat. And then one more force vector, that third force here. We know the magnitude is 1,200, and then the angle in standard position is 270. So on the negative y-axis. And then again, plus 1200 times the sine of 270 in the j-hat direction. And we'll see some things kind of nicely work out for us. All right, what do we know? Well, static equilibrium tells us that all of these things are going to sum to 0. So 0 in the i-hat direction, 0 in the j-hat direction. So I know that the sum of all of these forces must be 0. So F1 plus F2 plus F3 must equal 0 in both directions. All right, so let's use that information in order to set up a system of equations here. First thing I'm going to do is I'm going to add all of the horizontal components. So all of those I components and set those equal to 0. We are going to get x times the cosine of 45 plus y times the cosine of 150 plus 1200 times the cosine of 270. That's equal to 0. That's equation 1. Second, we are going to sum all of the vertical components. So equation 2 says x times the sine of 45 plus y times the sine of 150 plus 1200 times the sine of 270 is all equal to 0. I'm going to solve the system using substitution. So in the first equation, I'm going to solve for x, and then I will replace that in the second equation and solve for y. So let's do that work. Now, cosine of 45, we can evaluate, right? The cosine of 45, that's root 2 over 2. Use your unit circle. The cosine of 150, that is negative root 3 over 2. That second term is negative root 3 over 2y. And then the cosine of 270, this becomes super nice. The cosine of 270 is 0, so this third term kind of just goes away. And that's what we're left with. This is all equal to 0. So now I'm going to move everything over, try to get x by itself. So root 2 over 2x is equal to root 3 over 2y. To get x by itself, I am going to multiply everything by 2 over root 2, the reciprocal of root 2 over 2. So we get x is equal to, well, the 2's here cancel. So I'm left with root 3 over root 2y. And that's okay for now, because I'm just using this to substitute. So that's not my final answer. I need a number. But when I go over to the second equation now, everywhere I see x, I'm going to write root 3 over root 2 times y instead. Okay, so let's do that substitution. X is now root 3 over root 2y. And the sine of 45 is root 2 over 2. So something nice is going to work out there. And then we have the sine of 150, which is 1/2. So this is 1/2 y here. And then 1200 times the sine of 270. Well, the sine of 270, this is just -1. So this is just minus 1200. That's all equal to 0. Now I'm going to start combining like terms and seeing what we got. In that first term here, the square root of 2's cancel on the top and the bottom. But I'm also going to move that negative 1200 over to the right-hand side. And what we end up with is we end up with root 3 over 2y plus 1/2 y is equal to 1200. And so I'm going to combine those two y's together, and I'm going to keep the square roots kind of the way that they are. So this is going to be the square root of 3 plus 1 over 2. It's a really ugly fraction. Y is equal to 1200. And so what I'm going to type into my calculator to get y by itself, I'm just going to multiply by 2 over the quantity root 3 plus 1. And it looks like I'm getting 878.46 pounds. So that's our first answer, which is actually the second force here. So remember, that's the force in blue in the upper left corner of the screen. Okay, so once we've got y, then we can take that answer. We can go back to how we defined x, which was y times root 3 over root 2. So we're just going to multiply that by 878.46, and we can get x now. And once I've got all that in the calculator, I'm getting 1,075.89 pounds for x, right, for our second force, which is the first force in green, the one in the first quadrant there. So one approach using horizontal and vertical components. The next one's going to use the tail to head method. It is, I will tell you, significantly shorter, but it can be harder to see and set up. Okay, so then the next approach, again, goes back to the fact that this problem is in static equilibrium. So I can set up all of these force vectors in the tail to head method, and because this problem is in static equilibrium, it means that the three force vectors that we have going on will create a perfect triangle. So the sides will match up with each other. That's also how we can see static equilibrium. So I am going to kind of color code these forces and then start drawing them instead of the way that they're set up in the diagram, using the tail to head method instead. Okay, so in the previous way that we walked through this problem, I used green, blue, and purple, so I'll stick with that color coding there. So the first thing I'm going to do is I'm going to draw in my first force vector, which is just the one I have in green, the one that was originally sitting in the first quadrant, the way we had drawn everything the first time around. Okay, this first force vector, right, we're going to take the magnitude and the direction. That's really important, and I'm going to preserve that. And I'm just going to make it a little bit bigger so that our diagram can kind of match up here. Now, this force vector has an angle of 45 degrees with the horizontal. So this is force 1, and I know this angle here is 45 degrees. So I'm just going to mark that. Okay, tail to head method says this. Now we're going to use, we're going to draw our second vector from the tail of the first vector. So I'm going to draw the second force vector that we solved for, the one in blue, but I'm going to imagine like picking up that blue vector that's on the picture and just placing its tail at the head of our first vector. That's exactly what I'm going to do here. Okay, so then this time though, this one makes an angle of 30 degrees with the horizontal. So I want to make sure that when I draw this horizontal here, this is the 30 degrees I'm talking about. Okay, and if I've drawn this accurately, then what should happen, and I actually ended up drawing this a little too long, is when this problem is in static equilibrium and we've drawn the diagram correctly, it'll look something more like that. Right, so 30 degrees with the horizontal on that one. That third force vector, when I use tail to head, should end up matching up perfectly with my the tail of my first vector. Now, it's a little off. It should be like perfectly straight, but that's just because my diagram is a little bit off there. All right, but that's also what static equilibrium could mean if you guys don't want to look at it in terms of horizontal and vertical components. Okay, well, what do I know about that last one? That had a magnitude of 1200. And then I can start filling out more things. I know that that first force makes an angle of 45 degrees with the horizontal. So alternate interior angles tells me this is also 45 degrees. And so what happens is we get this interior angle of 75 degrees. And then one more thing to note here. Again, this goes back to the static equilibrium piece of our problem. This should be a 90-degree angle. And because this angle is 30 degrees, it's alternate interior with that inner 30-degree angle, I have my second angle of this triangle, which is 60. It's just 90 minus 30. And knowing that information, I can find the last angle in this triangle, which is 45. Sorry, 45. And now I have enough. Well, you didn't even have to do 180 minus that. You could have just done 90 minus 45. Okay, now I have enough information in order to use the law of sines. And we can use the law of sines. We don't have to worry about it. We're not solving for an angle here. And I can set up the law of sines like this. One option, 1200 over the sine of 75 is equal to the magnitude of force 1 over the sine of 60. Right? Plug that into your calculator. 1200 times the sine of 60 divided by the sine of 75. You get 1075.89. right? That same exact number that we found for force 1 using horizontal vertical components. And the same thing goes for force 2. Still going to use 1200 over sine 75, but now it's force 2 over sine 45. When I plug all this into a calculator, we get 878.46. So slightly shorter approach to the problem. Harder to see if you can't get that diagram right or you don't know where the 90-degree angles sit. Pick an option, work through the other static equilibrium problems like that.